Okay, let me do a brief introduction here. We are very privileged to have Dr. Ken Wolgemuth to come to talk to us about plate tectonic and particularly discovery of the plate tectonics, which witnessed God's wonderful design of this earth as a home for life for us. Dr. Wolgemuth graduated with a PhD in geochemistry from Columbia University and has worked 40 years of career in petroleum industry. And he came out and got a Colson Fellowship 2017, and also was given numerous lectures about creation. He co-authored 2018 paper on radiocarbon dating, published a book, this one, Grand Canyon Monument for Monument to an Ancient Earth. Huge volumes here. And the other day I was talking to him about what is the biggest discovery in geophysics, like biology. In the case of biology, it was Watson and Crick discovered DNA double strand in 1953. And I said, that's what we want to hear, Dr. Ken, and he got excited. So that's how we have the privilege to have him talk to us about this. Okay, Ken, take over.
Okay, well, I'm glad to be here again. I know I've been with you a couple of times, so I won't give other background comments about myself. Although this one is, I'll have a little bit of repetition that I'll build on some of the things that I said to you back in March. But let me get my screen shared right away and get that thing going. So. Okay, from what David has told me from a little bit ago when we tested it, that you can now see this.
Yes.
Is that correct?
Yes.
Okay, I'm going to get my full slide up and then we'll go.
Okay, everybody mute, please.
Oh, there you go.
I think it'll be appropriate that sometimes if you have some questions in between, or a few times I'll do a bit of a pause at logical steps if you want to ask questions, or wait till the end. I'll leave that up to you.
Plate tectonics, God's design for life.
So I made some comments about this in March, and I'm going to repeat those here in a little bit. I decided to have my main slide with the breakup of Pangea. So here's part of what Pangea was, the broken up into the multi-continents that we know today. And this is the period of about 60 million years ago. And I'll be playing that a couple of times during the talk. Let me get something going here. Push the right button. There, I got it going. Okay. I see these talks as that I'm giving them as creation story, that we have an ancient earth, and we certainly do have a magnificent creator in the way he put the earth together. Johannes Kepler is one of my Christians who's a Christians in the sciences, and I so appreciate the way he drew God right into his thinking, in that the chief aim of all investigations of the external world should be to discover the rational order and harmony which has been imposed on it by God. So he sees God involved in the processes all the time, and that I've adopted that same attitude. I appreciated reading this quote by R.C. Sproul. God is true whenever he speaks, whether it's in his word or his world. Both natural and special revelation are inerrant and infallible. So I appreciate that from R.C. Sproul in recognizing the value of special revelation in our understanding God's creation. So there's the Pangea supercontinent together about 180 million years ago. And then I will play it a couple of times during the talk. And you can see the North Atlantic opens, then the South Atlantic, and then the final big dash of India crashing into Asia to form the Himalaya Mountains over a period of about 20 million years. Life in the oceans is really dependent heavily on plate tectonics, and I have these a few slides that I'm repeating from my talk in March, in that all life in the oceans requires plenty of carbon and calcium and sulfur and phosphorus to thrive, because the plankton that are there and the corals that grow are constantly removing those components and those critical elements to be locked up in sediments, and therefore they get depleted from the oceans. Well, the reason they can get recirculated back into the continents is that those deep sea sediments get carried down into the continental crust, and where there is uplift of continental crust, that pushes mountains up, and then there is erosion and weathering that rivers eventually, after that weathering, carry those nutrients back into the ocean. So it keeps a cycle going. Here's one of the paradoxes that's been described related to tectonic activity. The recycling of the oceanic and continental crust holds the key. It's a balance against the continual massive loss of minerals to the seabed. Tectonic recycling replenishes the oceans with continental runoff by the reaction of water with upwelling magmas at the mid-ocean ridges, from Michael Denton. So these diagrams that are at the bottom here, I'll show a couple of times during this talk because our theme is plate tectonics. Plate tectonics in this process then promotes the biological productivity and helps to promote diversity of species that help to be a hedge against extinction. And we've learned that with the modifying of temperatures, that the plate tectonics helps maintain an equitable temperature that is necessary for animal life to exist, so we have a stable climate. Here's a comment from two authors that wrote a book, Rare Earth. It may be that plate tectonics is the central requirement for life on a planet, and that it's necessary for keeping the world supplied with water. These gentlemen, to my knowledge, are not in the faith community, so their worldview is likely as naturalists. So the nature of our continents and what mankind has understood about them. Back in the 19th century, it was understood that continents were just fixed, period, like this for long periods of time. But gradually, as we came into the 20th century, ideas began to come forward that there seemed to be evidence that continental drift had occurred. And we'll talk about some of those things related to continental drift. And then as I step through tonight, continental drift gradually developed with enormous amounts of data to bring us to a paradigm shift to plate tectonics. Early time, 1910 and 1912, the continental drift concepts were raised by a Frank Taylor and an Alfred Wegener. We had a milestone in 1926 when the American Association of Petroleum Geologists had a symposium in New York City to basically hear about Alfred Wegener and his ideas promoting the idea of continental drift. Geologically, right after World War II, we had an incredible explosion of the development of understanding the marine environment with marine geology and research. And I will draw on evidence from my institution, the Lamont Observatory with Columbia University. An incredible milestone that I will key in on was in 1967, where we had a compilation of data that had accumulated. And at the American Geophysical Union annual meeting in Washington, D.C., evidence was shown and demonstrated that finally answered lots and lots of questions and pulled things together to the paradigm change to plate tectonics. And my wife and I had the privilege of actually attending the 50th anniversary annual meeting of the American Geophysical Union, which was held in New Orleans in 2017. So toward the end, I'll make a few comments about that. The challenge of continental drift is because the continents are generally made up of lower density minerals. So it's dominantly granite and sedimentary rocks. And those thicknesses of the continental crust are up to 25 miles thick. Whereas it was known that the oceanic crust was significantly thinner, 4 to 5 miles thick. It was dominated by basalt igneous rock, was higher density. And the challenge was, if you think of a big, thick continent trying to somehow blast through or push out of the way oceanic crust, that concept geophysically didn't make sense, because in those days we knew nothing about the mid-ocean ridges, and we knew nothing about the production and the ocean building process, constructing process of oceanic basins back in those days. So the continents in 1926 were fixed as far as we knew, and they're, in this case, the thicknesses of the crust are in kilometers. So there are kilometers on the continents there from 30 kilometers up to 45 and 50, whereas all the blue is less than 10 kilometers. So that's the 3 or 4 miles that is typically the thickness of the oceanic crust. And then by 40 years later, we were able to consider those continents and put the arrows on the ocean system of mid-ocean ridges to demonstrate the evidence that plates had moved. So the symposium that I mentioned a little bit ago included Frank Taylor as one of the authors of one of the papers that was put together into a book published in 1928. And he made the point that he had exposed this idea of continental drift in 1910. Alfred Wegener had presented his theory in Frankfurt, Germany in 1912. And so for a period of time, it was actually called the Taylor-Wegener doctrine, or the Taylor-Wegener hypothesis. And then about 10 years later, there was a speaker at the Washington Academy of Sciences who said, "It seems eminently wise to retain as a working hypothesis the daring and yet majestic idea of Taylor and Wegener." So they were tied together. This was the first time that I have had the opportunity to realize that somebody beside Alfred Wegener had been thinking about this back in the 1910s. In general, at the time of this symposium in New York City, the Europeans had tended to accept the continental drift. Maybe that's partially because Alfred Wegener's activities over there and speaking. But as I will describe a bit from in a slide here, there was pretty strong pushback from American geologists. So here are some examples. From Stanford University, an author concludes that means of geophysical, geological, and paleontological reasoning, this should be rejected. Number 2, University of Chicago. Following are a few reasons why it seems to this writer that Wegener's theory is utterly untenable. Here was someone from Johns Hopkins that was somewhat supportive. Despite objection raised to the theory, it possesses a great degree of probability and is supported by considerable evidence. So he was at least sympathetic and listening more carefully. Here's another professor from Johns Hopkins University. This author objects to the Wegener hypothesis because the method of presentation is not scientific and the facts of geophysics do not support it. So boy, he really took a blast. They made a few boo-boos, which I call them oops. Frank Taylor assumed that the moon was captured by the Earth close to the end of the Cretaceous, which is about 70 million years ago. But now, these decades later, we recognize that that capturing of the moon was more back in the 4 billion years ago. So, and in the 1920s, they did not know the age of the Earth yet. The age of the Earth wasn't identified until the mid-1950s. Alfred Wegener himself made observations of Greenland related to Northern Europe. And in some way, he was looking at longitude, and I couldn't quite understand the logic, but he estimated that a year's drift of Greenland away from Europe was as much as 65 feet per year. Woo! The modern interpretation of the modern understanding, finally, once we got ways to measure that, that's separating actually at about 1 inch to 1.2 inches per year. So that was way, way off. One author speculated that it might take a whole century to understand and work out all these issues about continental drift, when in fact, we'll see here, it took about 40 years. So science was galloping along, and the events right after World War II are the reasons that those happened. So there's plate tectonics in 1967 as to where we're going eventually. I'm going to step through as many as about 10 specific types of evidence that they have that support plate continental drift, and then eventually plate tectonics. The shape of South America and Africa, fossils across that boundary, the Atlantic Ocean depth profile in the mid-ocean ridge, the rate of movement, the thickness of the sediments of the Atlantic, the first motion studies of the earthquakes that are happening at the mid-ocean ridge. The magnetic reversals is the big kicker that I'm going to show that really nailed it down. And that is reversals that are recorded in an oceanic crust along the mid-ocean ridges. I'll show the example of distribution of earthquakes and volcanoes and black smokers and hydrothermal vents that support this. I'll describe some of the data of Hawaii and the Pacific Ocean plate, coordinated and compared and verified by satellite data. And then I'll finally get some concluding comments about the Nazca plate that's on the west side of South America that is subsiding before or behind and under the Andes Mountains.
Saturday.
So for
Energy.
Is that a question? No, not yet. Okay.
Dave Luxford.
So indeed, South America and Africa do fit pretty nicely together with a little bit of overlap and gaps, but that really supports the idea. And as you saw in Pangea, yeah, they fit together, and then they were broken apart by activities down in the mantle. Here are 4 different types of fossil species that are described as being transitioning across the continents. The key ones, say, for South America and Africa would be this Cynognathus fossil that is found in both South America and Africa. And then another one is a Mesosaurus that is across from the southern part of South America and over into Africa, with some others in other kinds of fossils in the other southern continents. So here's the distribution of the Mesosaurus, distribution in South America that shows that it's there, and the distribution of finding it as a fossil in Africa as a piece of evidence that these were together at some point in time past. Well, the big explosion of a lot of study of the marine ocean basins came from, in fact, Lamont Doherty Earth Observatory, where the Lord guided me to go for my thesis work. The flagship that got started, the observatory was founded in 1949. This particular ship, which is referred to as the research vessel Vima, was commissioned to do this oceanographic work in 1953. And over that time period that it was still in use, from 53 to 81, it logged over 1 million nautical miles of travel in the ocean basins. In my case, I got on the Vima at one point in Cape Town, South Africa. So I was on that ship for one of these legs up here, and I disembarked in the Ivory Coast right there. And I remember from the Ivory Coast, I was sitting there and I got on the plane in the morning and flying back to New York City, and I went to a Broadway play that evening after going all that way home. A striking thing about the Lamont Observatory is that the director, Doc Ewing, recognized that just before he started the Institute, there were only about 100 deep sea cores that existed anywhere in the research community. And he, as he was operating the ships that were under the guidance of Lamont, laid down a dictum of having a core a day, that is, collect cores a day. So by 1956, Lamont had collected over almost 1,200. And today the core laboratory holds nearly 19,000 cores from deep sea sediments, which is a library available for all geologists around the world. The other ship, one other ship that Lamont operated, is the research vessel Robert Conrad. I was on this ship for 3 months, and overall Lamont has operated 4 different research vessels. I'll make a reference to one other one here in a bit, and estimated over 3,300,000 nautical miles in their research. Now, in my case, I got on the Conrad in Victoria, British Columbia. I sailed down across the Pacific, and the end of this bullet point here is about where Tahiti is. And then the ship came back for us and came in and then through the Panama Canal. So that was my experience of out collecting samples for my thesis project. Now, Doc Ewing was really unique in the way he operated his ships. As they were traveling, as they were plying the oceans at, say, whatever it is, 5 knots or 6 knots or 10 knots, however fast they went, he was always running a magnetometer. And the magnetometer is that about 6-inch in diameter and 3 or 4 feet long piece of equipment. It's towed on a cable off the back of the ship. So everywhere the ship is steaming, magnetic data is recorded. There's a gravimeter on board the ship, so that it was measuring gravity field. And it was always active with having seismic hydrophone detectors, and by use of an air gun, taking a blast of energy into the sediments to be able to view a seismic understanding of the thickness and the nature of the sediments that are on the seabed. So that was continuous while we were steaming along. We stopped every day, and every time the ship was stopped, cores were cut with a device that has about 1 ton weight here at the top of it. And then it's a long pipe that goes on down about 60 feet or 80 feet, depending on what the compactness of the sediments that they might find in that area. So this is lowered to the bottom, and then that ton weight basically pushes the pipe down into the sediments. So that's collecting cores. We had a tripod. We also lowered over the side that just short cores were collected of the sediment right on the surface. There were photos taken of the seabed. There were times they added heat probes to the coring device so they could check heat flow. And here's where my world is. This is a water sampler that's being attached to a cable that's lowered down into the water to collect water samples. So that was my world. Now, I've just highlighted this magnetic reversals up here because that's the data that is the real kicker that sealed the evidence of us understanding the nature and the rate at which plate tectonics was happening. So that will come into play here in a couple of different slides. That's a photograph of the Lamont Observatory. And this was the geochemistry building at the time that I was there in the 1960s and early 70s. This is the new geochemistry building that was built about 10 years ago. That's the core repository of some of those 19,000 cores that have been collected. And that map is showing the estimate of that 3 million nautical miles plus that the 4 ships that Lamont operated at various times had collected in plying the oceans. The result of plying the oceans gave Bruce Hazen and Marie Tharp the opportunity to get lots and lots of data of the depth of the ocean. And this world ocean floor map was compiled heavily by those 2 individuals and published in 1977. And then our focus here, in my focus now on some of the timing, is I'm going to look up and down the mid-Atlantic ridge or the mid-ocean ridge here. And then after a little bit, we'll really focus in on this central part in one of the components that helps to support this plate tectonic movement. So there's Pangea again, and let it play its thing, and seeing the North Atlantic open, and then the South Atlantic opens up, and India crashes into Asia to build the Himalaya Mountains. Now, the biggest thing that Taylor and Wegener had no idea was there was no mechanism to move these continents. That in the 1910s and 20s, nobody had any idea that what was going on in the mantle, as we eventually learned after the intensive study of the structure of the Earth with seismic data, and as geophysicists began to understand the nature of the Earth being divided into a liquid core, mantle rocks, and then a asthenosphere and crustal rocks at the surface. So the general model is that the liquid outer core is so hot, it heats up the mantle enough that the rock is not rigid, but behaves more like Play-Doh. And the result is that hot rock rises at where the mid-ocean ridge is, and then there are convection cells that are developed like this because of the pressure of the rising of that hottened or heated up mantle rock that caused the convection cells to move, and then new oceanic crust is being formed at the mid-Atlantic ridge and the mid-ocean ridges. So analogous to using a Bunsen burner and heating water in a beaker, that the hot water rises in the beaker and then it descends around the outside. So this was the dominant concept of a simple understanding of at least a potential driving mechanism that had the power to move the continents. So in the North Atlantic Ocean basin, the blue here are the older portions of the oceanic crust, 180 million years right at the edges of North America and Africa. And then 0 years is the new oceanic crust that's being formed up and down the axis of that mid-ocean ridge. That distance is 3,500 miles. So we take 3,500 miles, ends up as 220 million inches. That divided by 180 million years, and the average separation of North America from Africa works out to be 1.2 inches per year. We have the opportunity in these days, because we have the technology with satellites, that we can physically measure the rate at which they are separating even today. And that separation is 1 inch per year. So right in the range of this average that's worked out for previous times. Now, one of the pieces of evidence that plate tectonics is happening is the thickness of the sediments in the Atlantic Ocean and where the sediments are predominantly located. So I went on Google and I say sediment in the Atlantic Ocean Basin. And the very first paper that came up was the paper from Lamont. Maurice Ewing, Doc Ewing, as the first author. Bingo. And he had his co-authors, and this was published in the 1960s. And so the map shows the tracking of the VEMA and the other research vessels that they had data. And in fact, they said it was seismic reflection data from 750,000 kilometers of surveys that they could use as their database to develop and understand where the sediments were located. It's fairly thin along the mid-Atlantic ridge, the mid-ocean ridge, and most of the sediments are found right against the continents. And they made an estimate calculation that 73% are close to the continents, and the others are scattered out in the basins and a little bit on the mid-ocean ridges. This is a different version of kind of showing the same thing, but not quantitatively, in that the thickness of the sediments where this dark blue is located is less than 100 meters of sediment, and gradually the lighter blue could be 300 or 400 meters of sediment, transitioning into the green areas that are off the continents to maybe 1,000 meters of sediment, and then going up to 5,000 or 8 to 10,000 meters of sediment are just in selected basins right along the coast. Like down here is the basin offshore Brazil off Rio de Janeiro, or the Orinoco Basin or the Amazon Basin, and then all along the east coast of the United States. And in particular, our Gulf of Mexico is just a big sediment dump from all the sediments from the Mississippi River that's basically eroded the center part of our continent. So sediment thickness shows that ocean basin areas are young and don't have much sediment, and the sediments are in fact over against the continents. So there's the context now of the mid-Atlantic ridge, and we'll zero in on now some of the areas right in the center part there between Africa and South America. So that is that segment, and they've given variety of names of those fracture zones. In this case, this one is what's referred to as the Romance fracture zone. And the ship, the VEMA, is a ship that was active in identifying this particular fracture zone that's north of the Romance. And so it ended up having the name named after the ship of the survey of that particular fracture zone. Now, the white arrows I have there show the northern part aimed toward the left as you look at the arrow, and the southern portion to the right. Now, in this process, the red segments here are the axis, and the center of the mid-ocean ridge that's been ruptured. Okay, if these were normal fracture zones, it would suggest that the northern half of that slide is going to the left in relationship to the southern half. But you remember, that's not the motion that's taken place here, because you've seen the Pangea breakup, and it is South America and Africa breaking apart.
I'm away.
So that is not a normal fault. Instead, if we look at it this way, if that whole thing were a fault zone with a normal fault, the arrows would be that orientation. However, and then there would be earthquakes all across this whole red line. But the earthquakes out there in the middle of the Atlantic in this Romance fracture zone are only between these segments of the mid-ocean ridge. And down here, the earthquakes are occurring there. So if this were a normal fracture zone, the first motion of an earthquake here would be that way. But the first motion that's detected by seismologists at this fracture zone, the first motion is going that way. Okay, so it's showing that the African side and the South American side are pulling apart, and this is fractured in between them. And the first signal analysis of that seismic energy shows that this is not a normal fault, but it is referred to as a transform fault. So that is consistently true in all the earthquakes that occur up and down the mid-Atlantic ridge. Here's another diagram that kind of shows that, in that this is the ridge system right on the ridge, and there's the ridge system. And if this were a normal fault, the motions would be like that. But in this case, it is in fact South America moving away from Africa. And so the segment between these is referred to as a transform fault, not a normal fault. Okay, changing gears now to a very different topic, magnetic reversals. Do you have a question about that? That might be a spot that you want to ask a question. It's quiet, so I will press on. The nature of the Earth's magnetic field is that it is not completely stable with North Pole remaining at the North Pole, but the design and the way the magnetic field is developed, it has periods of being a normal polarity like we have the North Magnetic Pole today, or reverse polarity where it's turned, that polarity is turned southward. Geophysicists who study the magnetic field have all kinds of models of trying to figure out how in the world the physics of the dynamo and the interior and the outer liquid core change. And these are some of the models that are shown in terms of a period of time taking for that transition from normal polarity to a reverse polarity. These geomagnetic reversals have been cataloged by data from igneous rocks on the continents, where we can get good radiometric dating ages of them. And then when an igneous rock cools down that has the iron minerals in it, there is a residue signal of magnetic polarity that can be measured in those pieces of rock. So from hundreds of measurements of the orientation of igneous rocks, the geoscience community has established what is referred to as a normal polarity period and then a reverse polarity period. And you can see there are short ones in between. It is not regularly timed, it's sort of random. And then a dominant phase of normal and another significant phase of mostly reverse polarity. This is significant because this doesn't automatically say the same thing is going to happen on the seafloor, but that's the kicker that we're going to look at in a few moments. So when the magma is coming up from the mantle as the spreading takes place, when that igneous rock solidifies into a solid, and if the polarity is reversed, here that shows the band of the oceanic basalts in red. If the polarity of the Earth at that time window is normal, then the rocks preserve a polarity that shows that it's normal. So on either side of the ridge, there is banding of normal reversed, normal reversed, normal reversed that's identical on both sides. So for example, in this case, the normal coloring is the yellow with a plus sign, and the reverse polarity is green with a negative sign. So here is a period of time 4 million years ago when the Earth's field was reversed. 3 million years ago, the Earth's polarity was normal. 2 million years ago, the Earth's polarity was reversed. And today, the Earth's polarity is normal. So those successive bands of normal and reversed are propagated and remain in the signal of measuring data in the oceanic crust. This is a segment of the East Pacific Rise where Lamont did some research measuring that data from the magnetometer that was being towed behind the ship. In this case, the university was using a research vessel called the Eltanin, and the signal that I'm going to be showing you is some data of the magnetic measurements of Eltanin 19, which is that particular cruise and that particular transect across the East Pacific Rise. So here is the profile. It's identified as Eltanin 19 crossing. Please notice the ocean depth here in kilometers, in that right in the middle of the East Pacific Rise, the water depth is about 3 kilometers. Going away both west and east from the mid-ocean ridge, the sea level gets deeper down toward 4 kilometers. So the Pacific Rise is shallower than on either side. Now, the squiggly lines represent the magnetic anomaly that was recorded by the magnetometer as it crossed this transect of something like, it looks like 500 kilometers on either side. These identifiers of 1 and 1 are the example of a normal or a reverse polarity. So we can see number 2 on both sides of the ridge. We can see the polarity number 3 on both sides. That's what's significant. Now, here's the super kicker. In this case, this middle layer is measured the profile of the anomalies with the normal presentation that this end is the eastern end of the profile, and this was the western end of the profile. The trace above that is exactly the same data, but it's just been put on a transparent sheet and it's flipped over so that now the eastern end is there. So it's just reversed. The point is, we are looking at a situation where this peak that's in the normal, when you flip it over, it's right there. And these successive peaks are identical out both directions as they are examined back home in the offices. Now, so that's the profile. These are the profiles. The middle one is still the normal tracing. The upper one is the reversed. The third one down here now is a model that was built based upon the data that comes from the land-based data that I showed you a little bit ago I showed you 5 million years of the normal, reversed profile. And this matches so perfectly with the nature of the actual profiles that are there. So it's really significant that we're matching magnetic reversals on the continents with the magnetic reversals preserved in the oceanic basalts on either side of the East Pacific Rise and the Atlantic Ocean basin in the same way. So what's happening is the convecting mantle rock comes up. It ends up as freezing, solidifying, getting solid. It preserves the normal polarity and moving out away from the ridges of both sides. We have the normal, reversed, and likewise on the other side, normal, reversed, normal, reversed. That's the magic. What we have really here is almost a magnetic tape drive, if you will. It's a recording tape, right? In that these are recording what's happening to the Earth's magnetic field as it changes, and then it's recorded as the plates begin to separate and gets recorded and stays there, and we can measure it with the ship's magnetometer. So it was Lamont's data bank that demonstrated these magnetic anomalies of the Indian Ocean, the Pacific, East Pacific Rise, the South Atlantic Oceans had exactly the same symmetrical pattern out 1,000 kilometers from either side of the ridge axes. And here's what one researcher said. It hit me like a hammer. That hammer provides the decisive confirmation of seafloor spreading at mid-ocean ridges and prompts the development of plate tectonics. And this particular quote came from Walt Pittman somewhere there in the early 1960s or sometime in the 60s. And he was one of the researchers that I knew as I was there working in geochemistry.
Can I ask a question?
Yes. Now, please ask questions because this is the dominant kicker that hit that meeting in that AGU meeting in 1967 that basically persuaded and sort of it's the zenith meeting of understanding of the paradigm shift. Go ahead.
Okay, so this was spreading, you had said about 1 inch a year.
The Atlantic Ocean is about 1 inch a year. The Pacific Ocean basin is a little faster that I actually did show a couple of months ago, but I'm going to show it again. The Pacific Ocean, it's about 3 inches per year.
Wouldn't this be a very significant demonstration of an old Earth?
Oh, absolutely.
It would have to be traveling about 1,000 times faster, 1,000 inches a year to replicate the same process on a young Earth.
Yeah.
And you could almost visually watch it.
Yeah, the continents, if you want to try the 6,000-year-old Earth, for India would have had to be moving about a mile an hour. And there are no rocks. There are no rocks on the face of the Earth that would permit that. That's an imaginary rock.
The India situation, yes. I mean, they could say it just happens to look this way, but a symmetric, diametrically opposed, where you've got motion in two directions. I don't know how you can explain around that.
Yeah, there is none.
Yeah, I mean, India, yes, it certainly looks like, they could, they could just say, well, Pangea is just an illusion. Things do look like they lined up, but they could come up with some other example of lining, another way to do it that looks somewhat similar, but just doesn't demonstrate it. But a diametrically, symmetric movement in two directions where you can overlay them like you've just done, it can't be happenstance.
Exactly. And you're right on. Anytime that somebody on the young Earth community is wrestling with the magnetic field, they only permit about their diagrams I've seen only 3 or 4 reversals, and that's it. And then they abuse the idea even worse, in that the common theme is that the present Earth's magnetic field is declining with what is referred to as a 1,400-year half-life, which is not true. It's not true at all. But that's what is told the church. And that means if you'd extend that 1,400-year half-life back by 10,000 years, the Earth would be a neutron star. There would be so much magnetism to it. And that's so the Earth can't be more than 10,000 years old. Well, that's a nonsense statement, because the Earth's magnetic field does not decline with a half-life of 1,400 years. That's just plain false. And the Earth's magnetic field strength has been going up and down, and going through these reversals also. So that makes no sense. And you're right on.
I can.
Yeah.
Earlier, you show us slow speed, the development of Pangea into what present day we have a continent from 60 million years ago in a slow motion. Is that is constructed based on the knowledge we have on this reversal, and then
Exactly.
each movement of each continent against the others, right?
Exactly.
Is that correct? Okay.
Yep.
Thank you.
That's exactly where the speed and the relationships happen. Yep. Looking at the ocean basins. That's why this marine geology has been so significant. Yep. Well, now just comment about distribution of earthquakes. Mostly I've been talking about the mid-ocean ridges, and the mid-ocean ridges have all those yellow dots. These yellow dots are all earthquakes over about a 10-year period that have a magnitude of, I think it's over 3 or over 5, something like that. And where the plates are diverging like that, the earthquakes are always narrow, because they're just in that, breaking that rock apart. Any place where the rocks are coming together, such as the South American plate or the Nazca plate, actually, which is diving in under South America, there the band of earthquakes is very wide, as it is over there in Japan. The Pacific plate is diving in under Japan, so that's a wide band. Or down here where the big tsunami quake happened about 10 years ago, this is subduction of a plate, the Indian plate, that's going in under this portion of Asia. So it's a very wide band of earthquakes, and that's earthquake country down there. Or looking at India, when India crashed into Asia here, basically the whole China plateau has earthquakes in it because of that continual thrusting that India is still causing earthquakes up there. And we know about the earthquakes that happen in Europe, under Europe, and in this case, let's see, east there, Iraq here. So another example, well, okay, there are so many earthquakes around the Pacific and volcanoes and all these island arcs that are here. It's nicknamed the Ring of Fire. So that's a nickname that's been given to sort of the circum-Pacific events related to plate tectonics. In 1979, they began to discover some things that were unexpected. But once we understand plate tectonics, they can kind of come into play. They're referred to as black smokers. These are always hydrothermal events that are happening at the plate where the plates are being formed. I'll show a map here in just a moment where these are located. The gist is really hot water or seawater is migrating down into some of the sedimentary material near the ridge. And then there's so much heat coming up that is causing the rocks to sort of move upward at the mid-ocean ridges and then solidify. And as water percolates through there, the water circulates out and ends up coming through vents that form these smokers. I'll show a picture. Well, there you can see the black smoke coming up so easily. What's happening is the hot water is coming up at like 300 degrees Celsius, and it's loaded with minerals and elements in there because of the high temperatures that the water was experiencing. And then it encounters the cold water, and the minerals are dissolved in water, and then sulfides begin to precipitate. So these crusts and the growths around there are heavily sulfite minerals. There are hundreds of these around the world. I didn't realize there were so many when I found this map today. So they're basically on all the divergent plate boundaries that we see up and down the mid-Atlantic, the East Pacific Rise, Baja California, up along the west coast there. And fascinating, some of them actually have some life around them. And there's a lot of biodiversity at these hydrothermal vents. These are clams, more clams. Looks like shrimp in here, maybe. And look, there's a crab on that one. It's amazing. Okay, let's look at Hawaii. Kilauea volcano at Hawaii has been active for decades, and it's one of the longest active volcanoes. And we had a big set of events in 2018 when it was really pouring out lava. And there's some of the lava. We're going to look at the Hawaiian Islands as a chain of islands and the Emperor Seamounts that go on up to the Aleutians. Those are sourced because there's a hot spot down in the mantle, and it sends lava up through a plume that comes up through the asthenosphere and the lithosphere crust, and it pours out on the seabed, and then eventually comes and builds an island so that we can have the continual island building process happens at, in this case, it's happening on the big island of Hawaii for Kilauea. The plate is moving to the northwest, and it has done so for a long time. And so going from the big island to the islands to the northwest, they get older and older and older. In this case, then the 5 major islands themselves as the big island, and then the ages here that I'm presenting are numbers in millions of years from the potassium-argon radiometric dating method. And so it goes to 1.3 million years, 1.9, 2.6 is Oahu that has Honolulu. And then the Honeymoon Island up there to the northwest was formed 5.1 million years ago when this location in the Pacific crust was down over the hotspot. To look at the whole chain of islands now, the ages get consistently older and older and older. And eventually, past the bend, the ages from radiometric dating by potassium-argon get up to 80 million years old. So here we have a distance, and we have an amount of time, 43 million years. So that works out to an average of 3.2 inches per year. There we have a segment that's 1,500 miles. That works out to 2.6 inches per year. Then if we do a lot of little segments, we can check individual distances and times, and the range of movement ranges from 2.6 to 3.6 inches per year. And today with our satellite technology, as I mentioned with respect to the Atlantic Ocean basin, we can measure the movement of the big island of Hawaii right now over the grid that the geoscience community has established for the Earth, and the fact that the Pacific Ocean plate is moving to the northwest at about 3.1 inches per year on average. So here we see today the dominant movement of the continents is in the range of 1 to 3 inches per year. So the age of the ocean basins then, the youngest segment, there's an age scale down here at the bottom, and they're very young then at the mid-Atlantic ridge, at the East Pacific rise that's shown in red in this map. And basically the world's longest mountain chain is in this mid-ocean ridge system that wraps around the globe and goes into the Indian Ocean basin also. And as I step to the next, I've added now, or this adds the yellow and the green shade, which gets to 80 to 100 million years old of the ocean basin. And then finally, one that has some of the oldest portions of ocean basin. Basalts would be along Africa, North America, and then over in here in the northwestern Pacific Ocean basin. So we can see that on average, ocean basins are young of age, and it is the continents that are older. So I'll wrap up now with a few comments about the Nazca Plate, which is subducting in under the Himalaya, under the Andes Mountains. So this is the Nazca Plate on the west side of South America out to the East Pacific rise. And the Nazca Plate slab is moving to the east. There's a trench where that slab goes down under the western coast of South America. There is melting as that gets down to depth, and that results in some of the volcanoes that are formed up through the Andes Mountains. So here's an animation that helps to accentuate that idea with the ocean crust plate moving first eastward and then diving in under the Andes Mountains, melting the rock slowly and providing the lava suitable for volcanoes. Now, with that slab that's going down, that's indicative of, in fact, the epicenter of the earthquakes that are on the western side of that, where the plate is still at about sea level, are going to be shallow and near the surface. So the earthquake depth in the scale here is the younger band of 0 to 35 kilometers deep, and successively moving to the east, yellow, green, blue, purple, and red, the depth of the epicenter where the slippage and breaking is gets deeper and deeper because of that slab moving eastward and going downward. You'll remember earlier in the talk, I showed that the first and simplest understanding of the physical process of plate movement was driven by the mantle convection. In the recent number of years, the science community has identified a more dynamic kind of model of plate movement, in which they refer to as a sense of ridge push, in the sense that you remember here at the ridge for the East Pacific rise, the depth, the water depth is about 3 kilometers, but 1,000 kilometers away, the depth is about 4 kilometers. So there is a level of getting deeper and deeper and deeper. So there is a mild gravity component, if you will, helping to what they are referring to as a ridge push to move that plate to the east. Then the other concept that they've begun to understand is what is referred to as slab pull, when a cold, basically the cold plate is diving in under there, and as it dives, gravity helps to pull it down more quickly, and it's referred to as slab pull. This is one of the things that I learned because you, David, invited me to do this little piece of investigation to talk about the plates. So here's the concept, in that the slab pull has, and here the depths seem a little more consistent in the sense that, let's see, the purple ones are down to 30 kilometers, the blue ones a little deeper, and successively eventually down to red ones they have down maybe as far as 150 kilometers. All right. But that's that cold, the cold plate, if you will, sort of diving down underneath and attempting to pull the rest of the plate along with it. So that's my story. Continental drift hypotheses were proposed between 1910 and 1928. The 1950s, we had that explosive investigation of marine geology, with Lamont being one of the leaders in that activity. That 1967 AGU meeting was a zenith of understanding the concept and bringing plate tectonics right to the forefront, being accepted. In fact, one geologist I talked to who was studying his bachelor's degree at University of Washington said that his professor came back from that AGU meeting and told the class, or at least told this gentleman, he said, well, everything I've told you about geology has been a lie. We now know that. And then he opened up the idea of the plate tectonic paradigm change presented to this particular geology student. The magnetic reversals recorded by oceanic basalts about the mid-ocean ridge have really sparked this paradigm about the Earth and helped to trigger the plate tectonics shift concept of understanding how the Earth operates. The plate boundaries are nicely identified by earthquakes and volcanoes and black smokers and hydrothermal vents. And then my wife and I had the privilege of going to that 50th anniversary meeting, which was held in New Orleans. And they had a session just straight up called 50th anniversary of 1967. So I couldn't resist sitting there, since I had been in the one in 1967 with being clueless about all this stuff, because I had hardly had any geology by that point. And the biggest and fascinating question that was asked in that session was, for those of you that lived through that back in 1967, was it a long, slow, tedious process of comprehending ideas, or did they seem to shake together in a short amount of time? And my sense is I was hearing pretty much what Walt Pittman said, and like, man, this thing hit me on the, like a hammer, and like, hey, this really works. This plate tectonics concept that was first continental drift that had to be rejected because we didn't have any mechanism. Now with the molten outer core and the convection cells in the mantle, there's a dynamic process that can in fact produce the results and be the energy that drives it. And I leave you there with then a reminder that tectonics is identified as critical for the chemical recycling for life that we have on Earth. So it's part of our Earth, it forms the continents, and it gives us places to live. I've talked about an hour, a little longer than I wanted, but hey, I'm ready for questions. Thanks for your attention.
Thank you, Dr. Wolgemuth. Now we are open up for questions. Any questions?
Yes, great talk. I really appreciate, and had a little bit of knowledge about the Mid-Atlantic and Pacific, but seeing the data was very helpful. What is the period for this recycling of the chemicals from the plate tectonics?
That is one of the questions that I didn't really dig out this time. I looked at it. I looked at that a couple of years ago and I don't remember. So I'm going to make a note to myself. I'm going to make some guesses because
Yeah.
there are a couple of radioactive isotopes that are generated in the atmosphere because of cosmic rays bombarding. And so there are some isotopes that are being carried along in those surface sediments. And so there are some clues of that. And I'm gonna put it in the framework of, say, a few tens of millions of years. But I'm also going to dig in a little bit more, and I'll send an answer back to David Wu once I've reviewed it, because it's been too long.
Thank you. So, yeah, tens of millions of years, if that's.
Well, I mean, think about India crashing into Asia. That's not a 3 million year process. The moving in that case, India was moving faster, about 6 inches per year, but still the distance it's still over about a 15 million year period to crash. Now that's a different process. That's not subduction. That's, big football player crashing straight into big football player and the Himalaya Mountains get formed. So what the cycle is down deep, I would say a few tens of millions is a guess, but I said, I just haven't reviewed it recently, so I want to.
And this
check.
the cycling, what are the, just a couple things that it does to permit life? What?
Well, into the seabed, it's carrying calcium is taken up by all those shells. So calcium and carbon are incorporated into calcium carbonate. That's certainly, and incorporated in some organic material, okay, that would be carried along down with those sediments. So that's some of them. And then I'm sure phosphorus would be part of that process. So significant, maybe some of the nitrogen compounds that are related and necessary for life. But I first think of calcium and carbon and phosphorus. Again, one of those that I'll dig into.
Very helpful.
So thank you, Ken.
Ask more
again,
questions. Hey, Ron
Yeah.
Martin has his hand up.
Yeah, how do we know that there's no plate tectonics on the other planets, like on Mars? And what would they have to have plate tectonics there?
I think part of the issue of Mars is I don't think it's big enough to have a liquid core. So there's no magnetic field.
Hmm.
So it's size. So it's a mixture of size, and it might be mixtures of composition. I'm not sure. And then Mars is far enough away too that the temperatures are colder.
Mm-hmm.
But there is evidence that water was on Mars earlier, because they are finding sedimentary rock material, but there's no liquid water there now. And even if it's at the surface these days, the temperature is freezing, below freezing.
Yeah. And Venus is larger, I guess.
Venus is of suitable size, but Venus temperatures are so high there's no liquid water. So the atmosphere is just loaded with carbon dioxide and I think even I think even sulfur. Let's see what else. Particularly loaded with carbon dioxide. There was no mechanism to remove carbon dioxide from it, and then the temperatures are so boiling hot. So there's no liquid water.
So water is essential for plate tectonics.
Yeah. Yep.
Mm-hmm. Uh,
Ken, I have a
Yeah.
question.
Go ahead.
So before Pangea, how did we at this point know the Earth with 4.5 billion years old first was all rocky, uh, rocky globe, and then here comes the bombardment where the asteroid bring in water and eventually cover with all water. And then how does the continent Pangea form? How does a first piece of land kind of raise up from the ocean? Is that, am I asking the correct question? Do we know
That's a
beyond,
suitable question. Yes.
do we know anything
see-
beyond? Go ahead. Go ahead.
We see the concept that the Earth was covered with water. Then there'd be a time period about 3 billion years ago when what is described as proto-continents begin to form. And keep in mind that the concept of forming continents has to do with what's happening on the interior of the Earth. That is, when did it get a liquid core? How long did it take for this accumulation of rocky material for the interior of the Earth to be heated hot enough to have liquid rock to be volcanic? So that's one step in the process. And early protocontinents in one diagram I have begin to show some of those appearing maybe about 3 billion years ago. All right. And then gradually, once that got started, then the protocontinents would have additional size added to them as there's more differentiation of the separation of the lighter elements from the heavier, or I should say, the lighter mineral grains from the heavier mineral grains that are on the surface of the Earth. And then gradually these continents have built up larger from a central core. Like in the case of North America, it's the core of North America is dominantly northern Canada over toward Hudson Bay. So there's very old igneous and metamorphic rocks in that area, which is the core. And the Appalachian Mountains were added during the Paleozoic. And then a lot of the California and western side have been added during the Mesozoic. So then the continents grow bigger with time. So that's at least part of the answer.
Thank you.
Yeah.
Any more questions?
But I thought you might have been asking, were there other supercontinents before? And I did look up that question. And I saw a paper that did reference something about 7 supercontinents. But most of the names I haven't wrestled with enough to have them off the top of my head. One supercontinent name is Gondwana, and Gondwana tends to be once North America broke away, then all the that group of southern continents was Gondwana. So that was one that was sort of a portion of Pangea, but there were some prior to that, and the older ones are incredibly difficult to decipher because of they've already been then squashed into Pangea, and it's a incredible puzzle to put together when the earlier ones were. So I didn't build a table of one of those, but there was one paper that just said about 7, and they gave names, and I knew 1 or 2 of the names, but some of the names I had never run across.
Is there an explanation why it looked like you know, what we now call India was just a runaway, and it was moving, you know, 10 times faster than all the other
Yeah.
pieces.
Yeah, I did look into that, and we'll probably include some more. I have a paper here that I want to read in more detail. But what I did see specifically is that they've estimated that that one was moving probably about twice as fast as the Pacific. That is, it was moving at about 6 inches per year, but not 10 times faster. So
And
that would be 6 times
did-
faster than the Atlantic is separating. But yes, it was faster.
And did they give a reason behind?
Well, there will be a reason here. I didn't just get to read it again. I'm going to put that in a message to David, and then he can forward it to you. I don't want to. One thing I remember from reading an article years ago is they interpret that the mantle in that area had kind of multiple layers. So it was kind of layer on top of layer that were moving. So that's a little bit clue, but let me read it and then put my thoughts together, gather those thoughts and make some comments about that.
And then,
But the rate I read was about 6 inches a year.
and back to David's question, you know, your inclination is, okay, when the earth formed and it was all hot, that it should become uniform and consistent as a liquid would. But then remember, David, the asteroid impacts continued, and those asteroids are all dramatically different from each other. So it's gonna make pockets and of higher density and lower density, and it's going to make differentiation on the Earth. Once it started to cool down and was able to not act as a liquid again to keep it mixing, it would become pretty differentiated due to the impacts.
Is that Amy? Hello.
Yeah, that's Amy. So Chuck, was that a question or that was your comment?
No, it was just a comment, because, you know, I was thinking the same thing that you were, you know, why did we have continents? Why wasn't everything just, it was a liquid kind of, why wasn't it just uniform? What would have made one area higher than the other or whatever? And then I was thinking, well, you know, the super bombardment, large heavy bombardment, I forget what it was called, continued for quite a while.
Late heavy bombardment.
The late heavy bombardment continued for quite a while,
LHB.
and that would have caused a lot of differentiation on the Earth.
My sense that a lot of the differentiation is going to be happening on the rate at which the interior portion of the Earth would become molten. And then as it becomes molten, then the physical process of separating the heavier material, the nickel iron that is heavier, that would end up being transferred toward the center of the Earth and the inner core, in contrast to the aluminosilicate minerals that predominantly make up the mantle. So that whole big separation, I don't have a sense of the time frame. I've not looked up when they think the core actually got to the state of being molten.
I have one more question. North America and South America at the present rate of plate tectonic movement, are they separating or are they joining more and more together?
No, they're not joining more and more together. The Caribbean, the little Caribbean subplate is moving somewhat to the east. Now, distance between North and South America, I don't think is really changing that much, but they are not connected because they're separated because of that small Caribbean plate.
Hmm.
My sense is that they might be getting a little further apart,
Hmm.
but not significantly. Most of the movement is, in this case, most of the movement is east, is west.
Is the Indian continent still crashing?
Yes.
And the
Yeah.
Himalayas are going to grow and continue to grow.
Yeah. I've read that Everest continues to rise about 2 to 3 inches a year. Yeah.
A question, you showed a chart where most of the major earthquake volcanic activity was near plate boundaries, but not all. There are some significant areas where there's major activity away from that. Is that due to holes in the magma, or what causes that?
Well, the locations where the dominant earthquakes are near boundary, or volcanoes are near boundaries, the Andes Mountains are the best example of that, because that is a subduction zone boundary, and that does distinctly trigger volcanoes. The another area that triggers volcanoes, I'm going to go back and keep it in sync there. Okay, here. All right. So particularly volcanoes down here in the Andes Mountains are due to that subduction zone. All of the Aleutian Islands out from Alaska on that arc over to Russia, that is because of the Pacific plate is going in under.
But there's a large amount of volcanoes in Africa that looks like it's in the middle of the plate. I think that's what Mark's question was.
Okay. There are some, well, let me make another point about lots of volcanoes and tsunamis. This whole island arc here that's related to Indonesia is the Indian-Australian plate is diving in under this section of Asia that includes Malaysia and Vietnam in that southeast part of Asia. Now, these in Africa, okay, this point of Africa that represents what geologists call a triple zone, which would be right at the southern end of the Red Sea and at the southwest edge of the Gulf of Aden. The East African Rift System is sort of the third segment of that triple junction, but it was such that it has not split apart completely and broken up the African continent. And in fact, Kilimanjaro isn't really quite, it's somewhat east of that Rift Valley. The volcanoes that I'm aware of, that would be, let's see, there's a Mount Kenya. There's a few up through there. So they are at a somewhat of a rift valley. So there's some activity, but it's nothing compared to having a plate diving in under another plate as we have in the Andes.
So is it like a subplate with some differential movement? Not as much as the
Probably,
major?
yeah. Yeah.
Okay.
And of course, Indonesia is noted for its volcanic activity. And of course, the Japanese islands are volcanoes. Significantly volcanoes. Philippines has active volcanoes. Kamchatka Peninsula has volcanoes.
So do we have any more questions?
Yeah, yeah. Is water needed for plate tectonics to cool the lava as it emerges from the rifts?
I'm sorry, say that again.
Is water necessary for plate tectonics so it can cool the lava as it emerges from the rifts? Or what is
My sense is, let's see. I'm sure the amount of water that gets trapped in the sediments that gets carried down into a subduction zone has an effect on the behavior of those igneous rocks and those lavas. Now, to cool, what kind of rift zone? Can you give an example of a specific rift zone you were thinking of?
In the Atlantic Rift, there's lava coming up and pushing the plates apart. And in order to push, it has to be solid. So the water cools the liquid lava to make solid rock that's pushing them apart. Is that what's happening or not? That was just kind of a theory I had as to why the role of water.
Well, the role, okay, taking the Mid-Atlantic Ridge, it's clear that because of those black smokers that yes, water is getting down into the sediments and circulating there and being at very high temperatures coming out of those. So water that circulates down in at the divergent boundary is a factor in cooling those oceanic basalt liquids. Yes. I would say yes, definitely. Because you see those black smokers and those hydrothermal vents are in fact water that's circulating down and then coming out at high temperature and then cooling, playing a part in the cooling process.
Yes.
But the water that's there, okay. My model of understanding the predominant mechanism that carried the plates apart was really the mantle and the convection cells of the mantle. But my last couple of slides also reminds, and I heard about that idea of cold plate slab pull. And they feel the forces related to that cold slab going down into the mantle are somewhat stronger than what there might be from the ridge push to get things apart. So I don't see that. I'm not seeing water participating per se in pushing the water, but the water would be there, certainly a cooling agent.
Yeah.
and a solvent affecting the nature of these hydrothermal hydrothermal vents
Mm.
that one map verified that there are hundreds of them that have been discovered and observed.
Huh. Mhm.
Wherever that well, it was right here. Let's see. Probably pretty close here. There, look at those. All those red dots are some kind of a hydrothermal event.
Huh.
So there are lots of them.
Yeah. That's what happens to the water.
Now, some of it, yeah.
Yeah.
That's seawater that's seeping down in there, and then it gets hot,
Mhm.
dissolves minerals, and comes out, and then encounters that cold seawater, and bingo, sulfide, and there's sulfur involved down there.
Mhm. Yeah. Mm.
Again, just like Big Bang in astronomy and DNA, double-stranded, and the wonder of genetics, this geology, geophysics demonstrate once again that God causes everything to work together so that we can sustain life.
Yeah.
And it's another fine-tuned thing again.
I think that surprised me in this last 10 years, how much geology comes to play and how it was so finely tuned. 20 years ago, I wasn't aware that the water cycle was so well. I knew the rotor cycle was critical, but I didn't realize that the plate tectonics was that critical to the same level that I'm reading about now. Let's put it that way.
A major part of the plate tectonics is a release of oxygen, I suppose. You have oxidized minerals, and then when they're pulled underneath into the center of the earth, the oxygen is released by heat, and then we have the oxygen we need to breathe.
Yeah, the oxygen buildup in the atmosphere was distinctly. Of course, the oxygen, let's see, oxygen primarily comes from photosynthesis. So the big driver throughout Earth's history was photosynthesis getting started, and then a lot of oxygen was used up basically to form iron oxide because there was so much free iron in the oceans in the 3 billion to 2 billion to 1 billion years ago. Just lots and lots of iron. So a lot of oxygen was used up producing what are called banded iron formations, sucking up the oxygen. Well, once the amount of iron got tied up into oxides, then the excess oxygen got into the atmosphere. So the buildup of oxygen from like 2 or 3% of the atmosphere up to maybe 15 to its current 21% happened about the time of the Cambrian, happened about the time of 550 to 600 million years ago. Prior to that, oxygen level was very low in the atmosphere.
It sounds like the plates free up carbon dioxide, and then plants photosynthesize it and release the oxygen.
Exactly. Yeah. That takes photosynthesis.
And then without that, we'd be a red planet like Mars.
That's true. Yeah, you're right on.
So we have the atmosphere that produces storm and rain and water drained to the ocean, and together with the minerals and a bunch of things that plate tectonic would continue to recycle the nutrients, and so that the bottom of the ocean also have biodiversity, planktons and all that, photosynthesis produce CO2. Anyway, it was very complicated, complex life cycle, but amazing that we have plate tectonic and volcano.
Yeah. I had no idea that I would be so excited about my profession when I first got into geology. But it's taken me around the world and been just a joyride.
Yeah. So anyway, let's conclude our session here, and we want to thank Dr. Wolgemuth so much for a wonderful presentation. I learned so much personally. I'm sure everybody does, and I have a lot more other questions, but we will have another time for that.
And I have a couple of questions that are raised here that I'll do a little research and I'll send something to you.
Okay.
Dave, and you can share with the others.
So let me